Good morning, students. I am Muhammad Junaid Siddiqui. Welcome in the Bridge Design and Engineering subject. Today, we'll start the numerical on design of post-tension pre-stressed concrete I girder or T-beam slab bridge deck. So this is the first lecture. In this lecture, we'll determine the design moment and the design shear force for the design of the slab. Numerical is design a post-tension pre-stressed concrete I-girder slab bridge deck for a national highway crossing to suit the following data. Effective span is 30 meter, width of the road is 7.5 meter, footpath 1.5 meter wide on either side, thickness of wearing coat is 80 mm, live load is IRC Class AA tracked vehicle. Spacing of longitudinal girder is 2.5 meter center to center. Spacing of cross girder is 5 meter center to center. Materials are grade of concrete for slab is M25. Grade of concrete for girder is M60. The initial stress is 50 MPa. Adopt Fe415 grade HYSD bars. Pre-stressing steel 7 numbers of high tension strands of 15.2 mm diameter. Design the girder as class 1 type structure. Use loss ratio as 0.8. Pre-stressing stress is 1800 MPa. Design should conform to the specifications of the codes IRC 6, IRC 18, IRC 21, IRC 112 and IS 1343. This is the cross section of bridge. Center to center distance between the longitudinal girders are 2.5 meter center to center. These are the longitudinal girders. This is the cross girder. Width of the roadway is 7.5 meter with 1.5 meter footpath on either side. This is the top view of the bridge, in that the spacing of the cross girder are 5 meter and spacing of the longitudinal girder are 2.5 meter. So here the critical slab is the interior slab. So now we'll start with the cross section details. So first is thickness of girder. So as per IRC 18 9.3.1.1 page number 12, the thickness of the web shall not be less than 200 mm plus diameter of duct hole. So here we'll consider thickness of girder as 300 mm. Minimum thickness of the slab. So as per IRC 18 9.3.1.3 page number 12, the minimum thickness of the deck slab including that at cantilever tips shall be 200 mm. So here also we'll take minimum thickness of the slab as 200 mm. Assuming thickness of the deck slab could be taken at 50 mm per meter longer span of the slab panel. As here the longer span is of 5 meter, so thickness of the deck slab is 5 into 50, 250 mm, which is greater than 200 mm. Number of the main girder. So as per IRC 18 9.3.1.4 page number 12, in case of multi-beam arrangement, at least 2 cross girders, one at each support, shall be provided. For bridges having beam and the slab type of superstructure, the number of longitudinal beams shall not be less than 3 except for single lane and pedestrian bridges. So minimum longitudinal girders are 3, whereas in this problem 4 girders are provided. Design of interior slab panel. To design, we need the bending moment and shear force. Bending moment due to live load as well as due to dead load. Shear force due to live load as well as due to dead load. So we'll start with the bending moment due to live load. The critical slab panel is an interior slab panel. To produce maximum bending moment, one track of IRC Class AA vehicle must be placed at the center of interior slab panel. So we'll get the maximum moment. The width of the one track is 0.85 meter and the contact length is 3.6 meter. So this is the position of IRC Class AA tracked vehicle for a maximum moment. This track is acting as like a concentrated load. So as per IS 45624.4 page number 41, slabs spanning in two directions at right angles. For determining bending moments in slabs spanning in two directions at right angles and carrying concentrated load, any accepted method approved by the engineer in charge may be adopted. So from the note, the most commonly used elastic methods are based on P-Gird's or Westergaard's theory, and the most commonly used limited state of collapse method is based on Johnson's yield line theory. So here we'll prefer the P-Gird's theory. So as per P-Gird's theory, the shorter span MB is equal to W M1 plus mu M2, longer span ML is equal to W M2 plus mu M1, where W is concentrated load, M1 and M2 are the coefficients for moment along the short and long span. Mu is equal to Poisson's ratio for concrete, generally assumed as 0.15. The values of the moment coefficients M1 and M2 depend upon the parameters U by B, V by L and the value of K. So K is B by L, which is the ratio of short to long span of the slab. U and V are the dimensions of the load spread after allowing for dispersion through wearing coat. So U is the 0.85 plus twice of 0.08, which is 1.01 meter. Since here the dispersion is at an angle of 45 degree till the wearing coat only, and V is the 3.6, the contact length of the track is 3.6 plus the twice of thickness of the wearing coat is 0.08, so V is 3.76 meter. So aspect ratio is K B by L, so 2.5 divided by 5 is 0.5. So V by L is 3.6 by 5 0.752 and U by B is 1.01 divided by 2.5 is 0.404. So referring to P-Gird's curve, so here moment coefficients M1 and M2 for the K is equal to 0.5. So left hand graph is the coefficients M1 into 100, right hand graph coefficient M2 into 100. So V by L is 0.752, U by B is 0.404. So from the left hand graph, we'll see here the U by V value as 0.404 and the V by L value is 0.752. So it will give here the M1 into 100 as 9, whereas M1 equal to 9 into 10 raised to minus 2. So from the right hand side of the graph, we'll consider same V by L and U by B value. So here we'll get M2 into 100 is equal to 0.95, M2 is equal to 0.95 into 10 raised to minus 2. So M1 is 0.09 and M2 is 0.0095. Since MB is equal to W, M1 and mu M2. W is 350 kilonewton, load of one track of IRC Class AA. Therefore, MB is equal to 350, M1 value is 0.09, mu is 0.15, M2 is 0.0095. So we'll get it 32 kilonewton meter. Similarly, ML is W into M2 plus mu M1. So we'll put all the values and we'll get the ML as 8.05 kilonewton meter. As the slab is continuous, design bending moment is 0.8 into MB, whereas due to continuity, moment get reduced here by 20%, including impact and continuity factor is given by MB is equal to 32 into impact factor into continuity factor. So impact factor, here load will increase due to impact effect. So as per IRC 6208.3 page number 30, for class AA loading, 25% for spans up to 5 meter for the tracked vehicle. So here the impact factor will increase. The load will be increased by 25% due to impact. So MB is equal to 32 into 1.25 into 0.8. So MB will be 32 kilonewton meter. Similarly for the ML, so ML is 8.05 kilonewton meter. These are the movement due to live load. Next is the bending moment due to dead load. To get the dead load, here we have the slab as well as the wearing cord. So cross section of the slab will multiply with the unit weight of the slab material, will get the dead load. So dead load of the slab is 0.25, whereas 25 is the unit weight of the concrete as per IRC 6 page number 9. So we'll get the dead weight of the slab as 6.25 kilonewton per square meter. Dead weight of the wearing cord, so thickness of the wearing cord is 80 mm and 22 is the kilonewton per meter cube density of the wearing cord as per IRC 6 page number 9. So we'll get it 1.76 kilonewton per square meter. So total dead load is 8.01 kilonewton per square meter. Here our dead load is uniformly distributed over the complete slab panel. So here we'll take two values, K as 0.5 as well as 1 by K as 1 by 0.5 is 2. So V by L, since here the load is completely distributed over the slab panel, so V by L is 5 by 5 1 and U by B is 2.5 by 2.5, which is also 1. So as panel is loaded with uniformly distributed load, so U by B and V by L is 1. So referring to Pigot's curve, moment coefficients for slabs completely loaded with uniformly distributed load, coefficients is M1 for K and M2 for 1 by K. So K value is 0.5. So 0.5 K, here we'll get the M1 as 0.048 and 1 by K is 2. So to get the value of M2, here we need to see the 1 by K as 2. So we'll get M2 as 0.009. Total load on the panel is 8.01 kilonewton per square meter. So we need here the concentrated load W. So we have to multiply this with the area of the slab panel. 5 into 2.5 will get it 100.125 kilonewton. So MB is W M1 plus mu M2 into continuity factor. Since here the slabs are the continuous slab, so MB is equal to 100.125 into 0.048 plus 0.15 into 0.009 into continuity factor as 0.8. We'll get the MB as 3.95 kilonewton meter. Similarly, we'll get the ML as 100.125 into 0.009 plus 0.15 as a Poisson's ratio mu into 0.048 into 0.8 as a continuity factor. So we'll get ML as 1.3 kilonewton meter. Next is the shear force due to live load. As in the previously, for maximum bending moment, we have kept the track exactly at the center of the panel. Here we'll see the dispersion in the direction of the span. For maximum shear, load is kept in such a way that the whole dispersion is in the slab and near the support. So as per IRC 21 306.16.3 and 4 page number 55, dispersion of the loads along the span, the effect of contact of wheel or track load in the direction of the span length shall be taken as equal to the dimension of tire contact area over the wearing surface of the slab in the direction of the span plus twice the overall depth of the slab inclusive of the thickness of the wearing surface. Fourth clause, the dispersion is at an angle of 45 degree. So this is the cross section Width of the track is 0.85 meter. Thickness of the wearing cord is 80 mm and the thickness of the slab is 250 mm. So we'll get here the dispersion at an angle of 45 degree. So 0.85 is the width of the wheel plus twice the 0.08 is the wearing cord thickness plus 0.25 thickness of the slab. So we'll get it 1.51 meter. The load is kept at 1.51 by 2, that is 0.755 meter from the edge of the beam as shown. This is the position of wheel loads for maximum shear. Effective width of the load. So to get the effective width of the load, we have to refer the IRC 21 306.16 page number 52. So from that clause here we'll get the one formula. B effective is equal to alpha into A 1 minus A by L0 plus B1. All the terminologies are given here. So B effective is alpha into A 1 minus A by L0 plus B1. Width of the cross girder we have taken already 300 mm. Clear length of the panel is 5 minus 0.3 equal to 4.7 meter. As well, clear width of the panel is 2.5 minus 0.3, 2.2 meter. Therefore, B by L is 4.7 divided by 2.2, 2.14. So correspondingly, we'll get the value of alpha. So as per IRC 21, page number 53, here for the continuous slab, 2 and above value is 2.6. So alpha is 2.6 whereas B1 is 3.6 plus thickness of wearing cord will multiply with 2. So 3.6 plus 2 into 0.08 will get it 3.76 meter. Now effective width of the load on the slab. So B effective is 2.6 into A. So here the A is the distance of load from the nearer support, which is 0.755 multiplied by 1 minus A is 0.755 divided by L is 2.2 plus B1 is 3.76, will get it 5.05 meter. Intensity of loading is the load of vehicle into impact factor divided by effective area. So as per IRC 6 208.3 page number 30, so for tracked vehicles span less than or up to 5 meter, the impact factor is 25%. So intensity of loading is 350 into 1.25 divided by effective area is the effective length of the load is 5.05 into effective width is 1.51. So we'll get it 57.37 kilonewton per square meter. Consider 1 meter width. So we'll get it 57.37 kilonewton per meter. So now here we'll get the shear force due to live load as 56.9 kilonewton. Similarly, shear force due to dead load. So dead load intensity is 8.01 kilonewton per meter. Earlier we obtained it. So WL by 2 will get it shear force due to dead load as 8.81 kilonewton. Next is the design moments and shear forces. So design ultimate load moments and shear forces are computed by applying appropriate load factors to the service load and moments from IRC 6 table B.1 page number 91. Total design short span ultimate moment MBU is 1.35 into moment due to dead load plus 1.5 into moment due to live load. So we have all the values. So we'll put it here, we'll multiply it, we'll get 53.3 kilonewton meter MBU. Total design long span ultimate moment MLU, will get it 13.83 kilonewton meter. Similarly, total design ultimate shear force VU is 1.35 into VD plus 1.5 into VL. So We'll put all the values, we'll get it 97.24 kilonewton. So here in this lecture we obtained the design moments and shear forces.